Good morning. I'm Hussain, former professor, Department of Chemistry, University of Dhaka. We have been arranging lecture series on X-ray crystallography and solid-state chemistry. This is the 17th lecture on X-ray powder diffraction. The 16th lecture, we did talk about the different techniques, how to collect X-ray powder data, and then also the analysis of powder data. There are many information we can get from powder diffraction data about crystalline materials. That's what we talked. And in this lecture, we'll talk something about profile, fitting, and ripple analysis. A Dutch crystallographer named Hugo M. Rietveld, who developed this profile fitting and used neutron diffraction data. Well, what is profile fitting? We can always calculate calculated diffraction data for any powder. And then this is the calculated data, and we then fit this data on the observed X-ray data to verify our model of the crystalline materials. And there are variables which we include, and then the sum of weighted squared differences between observed and calculated intensity at every step in a digital X-ray powder pattern. This Rietveld refinement method requires rather good knowledge of approximate crystal structure of all phases which are present in the specimen. If we do not know the preliminary crystal structure knowledge or information, probably we could not do a Rietveld refinement properly. What are the input parameter to do the Rietveld refinement? As I say, the approximate crystal structure information, and this includes the space group, atomic position, site occupancies, lattice parameters, etc. With this information, then with the trial and error method, we start fitting. And when we see that the goodness of fitting is around 1 or so, we do believe that the model and the observed data fits well, and we get rather satisfied with the results. And people are doing this analysis for many crystalline materials, and also using this method to find the mixture of phases and the percentage of those compounds in the mixtures can be also obtained by this refinement. And this refinement is a convolution of Gaussian and Lorentzian convolution, and there are many different methods, but all that are a bit information to be put forward, and then analyze it, and then find the difference of observed and calculated data. Okay. Another approach we do go for these fittings, that is called fundamental parameters convolution. And that is, instead of using mathematical function, it builds some each diffraction peak by convolution of X-ray emission profile with the instrumental and simple contribution to the profile shape. This is an accurate peak profile is obtained and explicitly includes all aspects of the experimental and simple. There's a source of X-ray receiving slit with beam divergent crystalline sites, etc. So this is what this method is developing, and people are expecting to get better fit in this fundamental parameters convolution method. Okay, the next slide will show us a ritual refinement figure, and this is a example is barium zirconate powder, and the dot one is the observed intensities, count intensity counts, and the this line is the calculated one, and then you can see the difference of these two lines, and then you see it seems to be a very good fit by our model and also the observed data. Well, like every instrumental techniques to characterize materials, every technique has some limitations, and as usual, the X-ray powder diffraction data, though it is a very invaluable technique, but it has got also some limitations. What are the limitations? These are that if we don't have powder diffraction file in the ICD, Internal Center for Diffraction Data, then there is problem to analyze the experimental samples. If the material is not pure and it contains few other phases, that is also a bit difficult to analyze. We have to have some information to get an analysis. Another one is a very problematic. There are some X-ray powder diffraction data which are very close to each other. If such cases happen, then we see that we cannot possibly identify unambiguously the X-ray powder pattern. And these are primarily lithium niobate, many niobate and tantalite, and do also some other compounds such as rare earth elements. Their X-ray structure very similar to each other. Therefore, it is very difficult to analyze from the powder pattern. Moreover, there are systems where we got too many lines for powder pattern, and then this only the known methods to analyze the powder pattern doesn't work. Then we have to take other techniques. For example, neutron diffraction techniques. For example, electron microscopy to finalize the data to say correctly what it is in it. So there are some limitations also, which we have to know. Well, then we can also use high temperature X-ray diffractometer for using phase analysis or see the phase transition of solid materials. Well, in this XRD techniques, we do have same XRD, but then we have to have a simple container where we can heat. So therefore, this is a schematic diagram, very schematic diagram of a high temperature X-ray diffractometer. And at the same time, here in this picture, you can see that it's a commercial HT, high temperature X-ray diffraction, X-ray diffractometer. So it looks very simple if we look to this picture in the right, but come to this picture, you will see lots of parameters. So we have to adjust before we start taking our X-ray powder pattern and increasing the temperature. Lots of parameter. Here is the source of X-ray. Here is vertical parallel slits, and here is the detector with slits, and then you see platinum heating wire, and then platinum plate, and then we have a sample holder where we have to have a depth of sample about 0.8 millimeter to heat it and get the powder pattern in situ. Okay. Not only that, we have high temperature powder diffraction. If we if this simple holder where we have the possibilities of heating it, we can also have the possibility of cooling it and get the powder pattern during heating and during cooling also. And that what we say we need, we get very many information from there, the phase transformation, crystallite growth, and other dynamic processes that occur as materials are heated and cooled. An example of a high temperature powder pattern technique for a sample like calcium carbonate. What happened when we heat it with and then these are the X-ray diffractor pattern with temperature. This one is 300 degree, 500 degree, 700 degree, 800 degree, 900 degree, and then 1000 degree. We can easily see that calcium carbonate at 1000 degree splits to calcium oxide, and the peaks are very prominent. So here we can see how phase transformation is going on, or how the reaction is coming up. What are the product you can get from a single material when you heat or cook? Well, then here is a semi-qualitative quantitative analysis of mineral mixture. We get the mineral mixture and then we analyze these, and we can see that this is the PDF file of International Center for Diffraction data, and these are this red one is bromehite, and that is its chemical composition is this. And in this mixture, mineral mixture, 68% is this aluminum hydroxide. So bromehite. And then we have got iron oxide, we have kaolinite, we have anathas. These are the probable mixtures in the minerals. That what I say, that we can also analyze a mineral as we find it from hard cast, and then find out the composition of the mineral by using this X-ray techniques. And the data is the semi-quantitative data. Well, we can now have a distinction. What are the what do we get from powder diffraction and single crystal diffraction? We get from powder diffraction data the following: the characterization of crystallographic structure, size, and orientation in polycrystalline materials. What we need for bulk characterization methods, bulk characterization method sample needs to consist of about 10,000 randomly oriented grains, about 10,000. And the sample could be powder, thin film metals, polymers, etc. The method is a very quick method, and in some minutes you get the data and you can analyze it with the software now available. Though if we consider, say, in 70s or 80s, this analysis was done semi-automatically or manually. So at that time, it took lots of time and laborious as well as strenuous thing to analyze X-ray powder diffraction data. Now it is getting very easy with the software available. You can do it. About single crystallization, we can solve the complete three-dimensional structure of crystalline materials. Complete three-dimensional structure. What do I mean by three-dimensional structure of materials? That we can get atomic position accurately, we can get bond length, bond angle, we can thermal parameters, etc. But then the sample needs to be a single crystal. And we will talk about single crystal in next chapter, that is single crystal, how we deal single crystal details. And we can analyze inorganic, organic, and biological molecules of single crystals of inorganic, organic, and biological molecules. But in this case, that we need measurement time a little bit more than that of powder patterns. From hours to days, we need to have collect the data. So this is the main difference. Here in powder diffraction, it's very seldomly we can get a complete three-dimensional structure analysis. Okay. So this I said that we start now the single crystal, and the syllabus we are following. The 6th chapter of the syllabus is single crystal and data collection. And there we have seen for a single crystal, techniques of single crystals, growth, choosing of a crystal, crystal mounting and alignment, measurement of crystals, data collection, data reduction, and other things. So we need about 5 to 6 lectures to complete the above mentioned or content of the syllabus. And single crystal, what we get from single crystal. Single crystals are uniform atomic structure throughout the entire crystal. Uniform atomic structure throughout the entire crystal. How we prepare single crystal? By many phase, liquid phase or vapor phase or solid state techniques, we prepare single crystals. And there are very many different techniques also to prepare single crystals. And hydrothermal synthesis we can also do and find it. Now the question is that it is a very time-consuming synthesis, and preparing single crystal needs patience and lots of trial and error method to get a good single crystal from which you can collect data. And fortunately, we can immediately find out whether it is a good single crystal or not by doing a few experiments, and then whether we can collect data, single crystal data from this crystal and get a good three-dimensional structure that we can also find out. Crystal consists of two conserved atoms arranged in pattern that repeats periodically in 3 dimensions. That's what we discussed in the very beginning, that 2 aspects of that, periodicity and symmetry. We talked about periodicity, we talked about symmetry also in our previous lectures. Ideal crystal, what do we mean by ideal crystal? You see, an ideal crystal is a periodic array of structural units such as atoms, ions, or molecules. A periodic array. This is what is an ideal. We should have an ideal crystal where there is no disruption of periodicity. It can be structured by infinite repetition. We will say very long range ordering in this space. Structure can be described in terms of lattice. We talked about lattice, a group, and the group atom is the basis of this structure. It is rare that we find an ideal crystal signature. Very rare, almost not now. That we do get always defective crystals or crystals with impurities, and then we in the laboratory we start as much as we can to get a pure single crystal. Okay, we said there are large number of monographs and books, chapters where we will find how to grow a single crystal in a particular system. We are lucky that since single crystal is very difficult to get, therefore powder analysis gives us a good information about the materials. So what we do, that we take single crystal in the next lecture systematically, how we pick up a crystal, how we grow a crystal, and how we align a crystal. All these things we will take systematically. Up to this, today, we finish. And thank you very much for your kind attention for this lecture.